Hello everybody, this is Dr. Thunder. Today, I would like to show you how to solve a US high school physics competition question. This is question number 18 of 2025 F equals MA exam. So we have a particle of mass M who moves in the xy plane with potential energy U xy equal to k over 2 xy. If the particle begins at the origin, then it's possible to displace it slightly in some direction so that the particle subsequently oscillates periodically. So we want to find out what is the period of the oscillation. So the official answer is not really helpful. The answer is too simple to understand. So today I would like to give a very detailed explanation of this answer. So if we plot u equal to k over 2 xy, it looks like that. It looks like a saddle. But from this plot, it's not really easy to figure out the answer. So we want to give some mathematics here. So now we assume this particle has a distance d from the origin. So this is d, and then if from the angle theta with the x-axis here, so it's straightforward to figure out that x equal to d cosine theta and then y equals d sine theta. Now we plug these two expressions into u, so we get this expression. Then we simplify to be k over 4 d squared sine 2 theta. We define this as a u theta. Instead of u xy, we define as a u theta. So we need to find out a location where the potential energy is minimum, so that the oscillation motion can occur around this minimum. To find out minimum, we do a derivative of u relative to theta and then set it to 0. So the derivative of relative to theta from this expression, it will be k over 2 d squared cosine 2 theta. We set it to 0. Then we get theta either equal to 45 degree or 135 degree. Now let's look at theta. If theta equal to 45 degree, then from this expression we know that y equal to x. Then the potential energy at origin, which is x equals 0 and y equals 0. The u at origin is 0. Now assume that this particle deviate from origin slightly by delta x and by delta y. Then we calculate the potential energy at delta x and delta y. Remember the expression is here, so k over 2 delta x delta y. Because y is equal to x, then delta y equal to delta x. So we have k over 2 delta x squared. This is a positive number, so it's always larger than 0. So larger than u, the potential energy at origin. So this means if theta equal to 45 degree, then the potential energy at origin is the minimum. Now let's look at theta equal to 135. According to these two equations, then y equal to minus x. Again, the potential energy at origin is still 0. Now let's look at potential energy at a location that's slightly deviated from the origin, delta x, delta y. Then we plug delta x and delta y into the expression the expression of u x y. Then we because y equals to minus x, so delta y is minus delta x. So the potential will be minus k over 2 delta x squared. This is a number smaller than 0. Of course, we assume k is a positive number. Then the energy is less than U origin. So that means the potential energy in this case at origin is a maximum. So that means this is not a stable location for the particle. So now we have to take this theta equal to 45 degree, because when theta equal to 45 degree, the potential energy at origin is the minimum. So this is a stable situation. That means the oscillation can occur here. So if y equal to x, theta 45 degree, then x equal to y equal to square root of 2 over 2d. You can figure out from here when theta equal to 45 degree. Then u, again from this expression, u is, we can write in this form because this reminds us of the harmonic oscillator case. In a standard harmonic oscillator, if u is half k square x square, then the oscillation period is 2 pi square root m over k. So we use this expression in our case. So that means t is 2 pi m over this effective spring constant k here. So clean up to be 2 pi square root of 2m over k, which is answer D. So thank you for viewing. If you think my video is useful, please comment, like, and subscribe.